Now that we've seen the dot product and a handful of computations with the dot product, we're well equipped to talking about vector projections. So first, let's just define what vector projections are. We can give an intuitive definition, which I'll kind of show geometrically, and then we'll give like an actual expression or formula for being able to calculate vector projections. So let's let u and v, as always, just be two vectors. Okay, and we have, say we have u as the first vector and v as the second vector. We can talk about a vector projection of one vector onto another. We can consider the projection of vector v on to vector u. Okay, and so what do I mean by this? I mean, if we take v, we can consider a projection down to u, down to the other vector. You can see it's not the entire vector, right? It's just a piece of it. And this is what we call the projection of v onto u. And that's our definition here, is the projection of v onto u is this vector here. Geometrically, that's what's going on. We need a formula, though. And we can actually derive this formula using our notions, starting with magnitude. What would the magnitude of this be? And so just by notation here, maybe first let me talk about some notation. We say the projection of v onto u is the projection of v onto u. So we put the u as a subscript here. The subscript vector is the one that is being projected onto. The larger vector, not the subscript, is the vector that we are projecting. So the notation is, this is equal to the projection of v onto u. We write like proj sub u of v. Okay, and so now using the magnitude, let's kind of derive a formula for a projection vector. So let me copy my picture here. We have u, we have v, we have our projection. Right, and this vector in blue is the vector proj, the projection of v onto u. Now we can calculate this thing's magnitude, right? Well, with this interior angle theta, we know that we can form a right triangle here where the hypotenuse has length magnitude of v. There's some height here that we don't even really care about for the time being, some height y, and then this x distance here. But we know the base is just the length of the hypotenuse times cosine theta, right? And so that means the magnitude of the projection of v onto u is given by, it's the length, right? Because this base of the triangle is the length of the projection vector. So that means the projection, the magnitude of the projection is magnitude of v times cosine theta, where theta is that interior angle. And if you remember, let's recall that the dot product, u dot v, is defined to be the magnitude of u times the magnitude of v times cosine theta. That means we can write cosine theta as u dot v over magnitude of u, magnitude of v. So we can say that the projection of v onto u, the magnitude of this vector, is magnitude of v times cosine theta, but cosine theta is the magnitude of u times the magnitude of v all over magnitude of u, sorry, u dot v all over magnitude of u times magnitude of v. Notice the magnitude of v's simplify to 1. So the formula for the magnitude of the projection vector is u dot v over the magnitude of u. And so I'll copy this here just so it's concise and on one line. The magnitude of the projection vector of v onto u is given by u dot v times v, or over the magnitude of v. And here's some notation. The magnitude of the projection vector, we call this the scalar projection. The scalar projection, which we denote by comp for component uv. This is a number, which is the scalar projection, which is, whoops, the magnitude of the projection vector. So there's some notation for us. We call this the scalar projection when we write this as like the component of v on u, right? And now we want to use the formula for our magnitude to derive what how we can actually compute the vector itself, right? If you notice, we haven't actually explicitly said like, okay, well, here's how we find the projection vector. All we've done so far is come up with a formula for the magnitude and give it a new name. We call it scalar projection, right? And so what we want to do is, if we have that the magnitude of the projection vector is equal to u dot v over the magnitude of u, how do we obtain a vector that represents this in the direction of u? Well, we need to multiply by a unit vector in the direction of u. So let's multiply by a unit vector in the direction of u. So doing so is going to give us the proper formula for calculating the projection vector. So the projection vector of v onto u is going to be given by the magnitude of this vector times a unit vector in that direction, because then it will get us the correct magnitude and the correct direction. And so now we have 1 over magnitude of u times u, right? That's a unit vector in the direction of u. And so combining this, we get u dot v over the magnitude of u squared. All of this is just a number, right? This is all a scalar, and then times the vector u. And this is our formula for finding the projection vector, okay? So let me recap here. What have we derived? We've derived that the scalar projection, which we denote by comp v sub u, is equal to the magnitude of the projection vector, which is projection of v onto u, which we learned is u dot v over the magnitude of u. We also learned, this was the scalar projection. Now we learned the actual formula for the projection vector itself. So the projection of v onto u is the vector given by u dot v over the magnitude of u squared times u. And so this is how we actually find projection vectors, and here is their magnitude. You can see projection vectors become extremely relevant in physics. If you have a force acting on an object at a given angle, so like the perfect example is, imagine you have a little wagon here with a handle, and you're pulling the wagon this way, right? Well, the force that's being applied is at an angle. Here would be a vector representing force, right? It would be at the angle that you're pulling the little wagon here. The force would not be parallel to the direction that the wagon is moving, right? And so to find the force, or even to calculate work, say, if you want to calculate the work that it's going to take to move this cart or wagon in the horizontal direction, you can't just look at the force vector here. You've got to look at the projection vector of force onto the horizontal axis, because it's going to move. If you assume this is on flat ground, it's going to move in line with the horizontal axis. And so you need to look at a projection vector to do that. And we'll actually talk about work here. So maybe while I'm in this realm of like physics application, let's talk about using projection vectors and dot products to calculate work. Okay. So here's a physics application. And it's calculating work. Okay. So when we have, so remember, in general, work is force in newtons times distance. It's how much force you apply and for how long you apply it, and distance can be in meters, right? And work is given in joules. Joules are the units here. Units are joules, which are Newton meters, right? And so work, if you remember, is if you've taken like EP1 or EP2 or anything like that, work is it gives you a value that describes like how much work you've exerted to push, say, like a given object. How much force did it take you to push an object this far? Or how much force did it take for an object to move a given distance, right? And so we can calculate force or calculate work in a vector setting, because we can represent force as a vector. So because force is something with both direction and magnitude, right? You apply force in multiple directions or in many different directions, and you also apply different like strengths, right? Different magnitudes of force. And so when we have a constant force, so let's let F be a constant force applied to an object. so that it moves from point P to point Q, the work done is calculated by W equals the dot product of force with the direction vector PQ, which can be calculated. We know the dot product is the same as the magnitude of F times the magnitude of PQ times cosine theta, where the force F is acting on the object at an angle theta. So let's look back to this picture that we have here of like a wagon, say. We have a wagon with a little handle and some kid is pulling the wagon, right? And let's say it starts at point P and somewhere down the road is point Q. And we're going to exert a force F in a direction not in line with the vector PQ, right? The vector PQ is going to be this vector in red here. This is the vector PQ, and then we have our force vector. And you'll notice this force is not acting on the wagon parallel to the vector PQ. It's acting at some angle with theta here. And so we can calculate the work done to push or pull the cart from point P to point Q just by taking the dot product. All you have to do is express force as a vector, and then you express your PQ vector using terminal and initial points, and then you can calculate the dot product either with the standard definition, or you don't even have to be able to express them as vectors. And that's what this is saying. This formula up here is saying all you need to know is how strong the force you applied is, and you need to know how far you're pushing it. And you also need to know at what angle are you applying this force. And you've calculated the work. And so I think that's where I'd like to break from here. Because I didn't explicitly go through an example of calculating a projection vector, but you can see these are all things we're very comfortable with by now. By now, we're very comfortable with taking a standard dot product, and hopefully we're very comfortable with calculating magnitude. And so all we have to do when calculating, like on the homework and stuff, what we look at is we just calculate this number, and then we multiply the vector u by that number, right? This is all a scalar, i.e. a number. And so when finding projection vectors, the heavy lifting is calculating whatever the scalar is going to be. Well, and then you just multiply it by the vector u that's already given, and you're good to go. And so now we've seen vector projections, and we've seen a little physics application about calculating work here. So that's where I'd like to wrap it up for the dot product. And then in the next set of videos, we'll go through and kind of an analogous format that these last two videos have been in, but now we'll do it with the cross product, where, remember, the dot product spits out a number, right? The dot product is an operation that takes a vector and another vector, and the dot product gives you a number. What we're going to do with the cross product is we're going to take a vector and another vector, and then what the cross product will spit out is a different vector, a completely different vector. And we'll see, we'll go through kind of a similar setting, like how do we calculate it? What are some properties it exhibits? What can we do with the dot product in math? What can we do with the dot product in physics, and or the cross product, excuse me. And we can get kind of an introduction to what the cross product is used for, just as we have with the dot product. So, and that is all for the next video.